John Powell the physics guy. John science is cool. John Powell the physics guy.
Okay, let's do potential energy classwork. So as always, we start reading the equation, or the problem. A cart weighing 10 newtons is pushed 10 meters on a level surface by a force of 5 newtons. What is the increase in potential energy? So there's a lot going on here, so let's just jump right in. We got a cart weighing 10 newtons, so I already did the work for you. That's mass times gravity. So if I wanted to, I could find the mass of the cart, but I don't think that's needed. So it's 10 newtons. Distance is 10 meters. And force applied is 5 newtons. So that's the big difference here. So when we're talking about work and stuff like that, that's the force we put into it. So force of gravity is going down, but it looks like we're applying a force this way. So, and if it's moving to the right, then that is the work, not gravity. Just important to point that out. But anyways, so we want to know what the change in potential energy. So we're not even talking about work in this case. So that was last lesson. We want to know mgh. Well, again, we already got the force of gravity, so 10 newtons, mass times gravity. But if we want to know the change in potential energy, mass and gravity is not changing. The only thing that could change is height. But in this case, level surface. So change in h is 0. Therefore, the change in potential energy and gravitational field is 0 joules. There's no change in potential energy because we didn't change our height at all. So this is good practice number 2. In each of these, they're giving us like the mass and the distance above the ground. So we're just going to assume all these are times g. So, again, potential energy is equal to mgh. So I'm just going to go ahead and do all our 50. I'm just going to leave, I'll put it in there. 50 kilograms times 0 meters, because it's no height up. 2 kilograms times 10 meters. And then 10 kilograms times 2 meters. And I got 6 kilograms times 5 meters. So I've got 50 times 0, it's 0. 2 times 10 is 20. 10 times 2 is 20. And 6 times 5 is 30. Now each of these I would take times gravity to get it into joules. But you can just see that D is the winner. It's the highest number, 30. So that has the greatest potential energy with respect to the floor. Okay. So this is a good, fun, long one. A mass resting on a shelf 10 meters above the floor has a gravitational potential energy of 980 joules with respect to the floor. The mass is moved to a shelf 8 meters above the floor. What is the new gravitational potential energy of the mass? Oh boy. So let's just start with height is 10.0 meters here, and when it's at that height, it has a potential energy of 980 joules. It is then moved down to a height of 8 meters, and it wants to know the potential energy at that height. Well, there's 2 different ways to go on this. I'm going to show you the true long way. Okay. So we know potential energy, mgh. So in this case, we have h, we have potential energy, we know gravity, but we don't know the mass. And we're going to need to know the mass if we're going to go over here because we have the height, but we don't have the potential energy and we don't have the mass. So let's just go ahead and solve for the mass. Just make it clear, gonna divide both sides by GH so I can get these to cancel out. Okay. So I have potential energy over G is equal to GH times mass. And then 980 joules times, divided by 9.81 meters per second squared times 10 meters is going to be our mass. And put that in your calculator, 9.99 kilograms. So then we can bring this guy all the way up here. 9.99 kilograms times gravity times the new height, 8 meters. And you plug that into your calculator. Oops. Seven, 8.4 joules. Okay, so that's the two-step problem, but you can do it. Now, if you're good with math and you're just able to like look at this and realize it was at 10 meters and now it's at 8 meters. That is 80% of what it used to be. So, because this is a linear problem, MGH, I know that if you're multiplying by a constant amount, so you could have just done the original 980 joules times 80% of that, because that's 80% of that height. If you do that, you get the exact same answer with less steps. But again, if you're not comfortable with that, please do the long way. But just showing that there are shortcuts, and there's several ways to do problems. Okay, so last one, dealing with potential energy due to gravity. So what mass would have a potential energy of 490.5 joules at a height of 10 meters? So let's start with our knowns. This time they give us the energy joules, height 10 meters, and we want to know the mass. MGH. Okay, so yeah, once again, I'm gonna divide by GH. Oh, so it's kind of like doing the same problem again. Apologize that it's like 2 in a row. But, whatever. It's good practice. Sometimes you just need to solve for the mass. So I've got 490.5 joules all over 9.81 meters per second squared times the height at 10 meters. And you do that math, and you get 5 kilograms. And it should just make sense, because if you look at the last problem up here, we had a height of 10 meters, and it was 980 joules. Again, we're at 10 meters here, and we see that the amount of energy is approximately half of what it was. So it totally makes sense. Half the mass, half the energy. Alright, moving on to springs. A spring has a constant of 120 newtons per meter. How much potential energy is stored in the spring as it is stretched 0.2 meters? Okay, so now we got different stuff. 120 newtons over meters. X is 0.2 meters, and we want to know how much potential energy is stored in that spring. potential energy is equal to 1/2 kx squared, or 1/2 120 Newton per meters times 0.2 meters squared. So very important to know. Like, a lot of people are going to forget the square. It just, I guess, it takes practice just to always remember to get that square in there. So you plug that into your calculator, and it's also great practice just using your calculator. Make sure your answers are matching mine. So 2.4 joules. So now let's do, when a spring is stretched, again, 0.2 meters from equilibrium position, and now it possesses an energy of 10 joules, what is the spring constant of this spring? So this is similar to the last one. I see I'm stretching it same distance, but now it has a lot more energy, so I'm expecting this K value to be a lot bigger. So, but let's see. X is equal to 0.200 meters. All this means is I'm gonna have more significant figures, right? Now they give us the potential energy of the spring, 10.0 joules, and we want to know K. So, boop, 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 boop. 1/2 kx squared. This time we're trying to solve for K, so I'm just going to take this in steps, make sure we're happy. If I take this times 2, these 2's will cancel out. Just to be clear, 2 times the potential energy of the spring, now I have kx squared. Now I need to divide by x squared on both sides. Boop. And we are happy. We got K equals 2 times the potential energy of the spring all over x squared. So let's substitute with units. 2 times 10 joules all over 0.2 meters squared. I like to put everything inside parentheses when I square it, just to help me remember I need to square the 2. I also need to square the meters. So when you're doing unit checks, you know, it's just a good habit. So I got 20 joules over. Actually, I'm just going to give the answer here. If you put this in your calculator, you're going to get, what do you get? 500 newtons over meters. So yeah, that made sense. This K value is quite a bit larger than the problem 5. So it's always a great check. You just ask yourself, does this problem make sense? Okay, almost there. A spring with a constant of 4.0 Newton per meter is compressed by a force of 1.2 newtons. What is the total elastic potential energy of this compressed spring? So let's see, K equals 4.0 newtons per meter. Force is 1.2 newtons. And we want to know what the spring. Okay, so PE is 1/2 kx squared. Uh-oh. Did I miss x? Oops. Is there no x? Well, this is a 2-step problem, and I believe you guys should be able to do it. And I know it's a little more difficult, but you have to go back now a couple units. Remember, we have other equations for springs, so we know that the force on a spring is equal to kx. So we can get our x dividing by k on both sides. Oh, that's great. Okay. So X is going to be 1.2 newtons over our K, 4.0 Newton meters. X is going to be 0.3 meters. Now, we can do this. What did I say? 4.0 Newton meters times 0.3 meters squared. I'll put that in your calculator and you should get 1.8 joules. So again, yes, I mean, this was a two-step problem and would be like one of the harder level ones on your Regents exam, but I believe you can do it. So last one, let's do it. Spring A, okay, this is good. Spring A, I cannot talk. Spring A has a spring constant of 140 newtons per meter, and spring B has a spring constant of 280 newtons per meter. Both springs are stretched the same distance. Compare the potential energy stored in A, compared to the potential energy stored in A, the potential energy stored in B is, so I'm going to put B on top. What we're doing is going to compare B to A. And both these are going to have PE of the spring B, PE spring A, 1/2 K x squared, 1/2 K x squared. So they are stretched the same distance. They both have 1/2, but the only difference is their K values. So B has 280 newtons and A has 140, newtons per meter. So B is 280 newtons per meter and A is 140 newtons per meter.
Interruption to clarify the previous announcement.
Okay, so 2 times as much. Thank you.
Until further